Hello everyone, welcome back. How are you all doing? Hope you're doing extremely good on a Navaratri weekend. All right, awesome. So if you can hear me, I'll get started. So a little about me. I'm Sai Avinash, and I'm a studies PhD at Google Dublin. In this lecture series, I'd be solving problems live, like math problems live, or any other. I'll pick a topic. Like for example, in my previous videos, I've done strings and ad hoc problems for greedy and so on. And I'll be solving them live in front of you. It's just a problem solving and session where you can discuss with me in the live chat, and if you have any doubts, you can ask me as well, or any other questions, I'd be happy to answer them. And yeah, again, a little about me. I'm only rank 4 at CodeChef. I'm 7-star coder there. I'm Max International Master at Codeforces. I'm previously also interned there right now, and I'm also snagged on finalist. The subjects that I take are discrete maths, dynamic programming, graphs, and a lot of other combinative programming topics. So don't forget to use the code SciLive to get a 10% off on the Unacademy Plus subscription. So do subscribe to the Telegram channel to get live updates on the latest classes so that you don't miss out on any. Yeah, and don't forget to if you find the video useful after watching the video, of course, don't forget to drop a like and to share it with your friends if you think it's going to be useful to them. And don't forget to subscribe if you want to get updates on the latest classes. Yeah, it's easy to miss if you subscribe. So let's solve problems. Let's look at the first problem. I'll start off with a really easy problem. That's the problem. Yeah, here it is. All right. It's a two-way problem, so it's pretty straightforward. But let's solve it. Let's try to solve it in an efficient way as well. So what do we have here? Polycorpus has a ribbon of length, and he wants to cut the ribbon in a way that fulfills the following conditions. After cutting each ribbon, each piece should have a length A or B or C. After cutting, the number of ribbon pieces should be as long as possible, as high as possible. Awesome. Let's look at it. Let's look at what he means first. Let's look at what he means. Also, can you just confirm that you can hear me in the live chat? So I know that things are good. Things are good. Awesome. People in the live chat, you need to be subscribed to actually hear talk in the live chat. So can you hear me? Can you please let me know in the live chat so that I can get started with the problems? Awesome. All right. So what does the question ask? What does the question ask? So question says you're given a number n. Man, okay. And you can either divide it into A's, B's, and C's. You're given A, B, C. So essentially given A can choose x times, B can choose y times, and C can choose z times. So you need to maximize x plus y plus like ax plus by plus cz equals n. You need to maximize x plus y plus z. Meaning you need to split n into like groups of 2's. Like for example, if n is say 100 and you're given 3, 4, 5. So you want to split 100 into groups of like 100 into several parts. Each part should be either 3, 4, or 5, and the sum of the numbers should be 100. For example, you can split this into 3 and say 4, 4, 4. Now you have 15 gone. Now you can choose 17 5s, 5, 5, 5. Like 3 is gone from 100 becomes 97, 92, sorry, 93, 89, 85. Now we have 17 5s. For example, if n is say 15 and you just have 3, 4, 5, you can choose 5 3s, 3, 3, 3, 3. But you can also choose 3 5s, 5, 5, 5. You can also choose, I guess that's it. You can choose 3 4s and a 3. So with this you're getting, it's divided into 3 parts. With this it's divided into 4 parts, and with this it's divided into 5 parts. The question asks, what is the maximum number of parts you can divide it to? After cutting, the number of ribbon pieces should be maximum. So since this is the best you can do, like 15 is divisible by the smallest number, so which is 3, and so you need to print the answer 5. All right. Hi Arunachalam. Good to hear that. So anyway, let's get started. So can we do a greedy approach? Let's think about a few approaches to this problem. Let's think about a few approaches to this problem. What do we have here? Say you have 100, for example. One option is to like here, say you fill it with a lot of 3's. How many 3's can you fill 100 with? You can, like say A is 3, B is 4, C is 5. 100 you have here. You have 100 here. All right. First you try, let's look at the greedy approach and let's see why it fails as well. 100 you have 3's. So try to fill it with as many 3's as possible. You have 99 here then. 99 here, right? Now what is remaining? 1 is remaining. 1 cannot be filled with any of these. Let's try another number, 96. This passes. 96 requires 32 3's. So basically our goal, if you want to divide it to maximum pieces as possible, your pieces should be as small as possible. That's your ultimate goal, right? All right. We can't divide into 19. We can't make 33 into 3 because you are left with 1 and you can't make 1 with any of them. So you try 96 and like 32 into 3. Yes, you've got it. Like you have 4 which can be filled. Awesome. But there might be cases where this might not be so optimal. For example, I'm thinking of an example. So you have 5, 6, 7, and say you want to make, well, it's kind of hard to get an counter example. So this might work, but like let's look at a more concrete example. Like one greedy algorithm could be try 100 and keep subtracting, given the number, you're given A, B, C. You keep subtracting the smallest number till you can make something out of the rest. But that would be a bit costly, right? So let's look at a more concrete way to do it. Look at the constraints. N is up to 4000. All these numbers, N, A, B, C, are up to 4000. Right? 4000. Which means, basically, what's our mathematical formula here? X into A plus Y into B plus Z into C is equal to N. Right? And you want to maximize, there are X parts of length A, Y parts of length B, Z parts of length C. You want to maximize the total number of paths, which is basically x paths plus y paths plus z paths. You want to maximize this number. So what we can do is we can just brute force on x and y, meaning since x and y, z, all of them have to be less than 4,000, right? Because like you can divide it into at most 4,000 parts. So x comma y is less than or equal to 4,000. We know that if we fix x and y, we can get z directly. Like we know x into a, we know y into b. We know what c is and we know what n is. It's easy to get z by solving that equation. Correct. Is this clear? Is it clear where I'm going with? So once we do this, so we iterate from x from 1 to 4,000, y from again 1 to 4,000, and we can find z directly. And then we update our answer with answer is initially 0, the maximum number of parts is equal to, we update max parts with x plus y plus z. Like this, like the maximum of all such x plus y plus z will be our max parts, right? Is this clear? Any doubts please let me know in the live chat. Arunachalam, yes, wait, has it started? I don't know. If it started, yeah, then I should probably participate, yes. Yeah, I'm going to participate here. Yes. Yep. No doubts. Okay. So let's just code this off. It's very straightforward, right? Just remove the scrap. Awesome. What are you given? Simple. You're given int n comma a comma b comma c. C n a b c. Int x equals 0, x less than or equal to n, x plus plus. For int y equals 0, y less than or equal to n, y plus plus. So int, what would cz be? What would c into z be? N minus a into x minus b into y. Cz should be a multiple of c. So wait, so another condition is if cz is less than 0 or cz modulo c not equal to 0, continue. If it is, then int z equals cz by c. Answer equals max of answer comma x plus y plus z. Right? Awesome. We initialize our answer with 0 and we print our answer. That's it. That is sufficient. Is that clear? In the question, it is guaranteed that at least one correct ribbon cutting exists. Like there's at least answer is going to be updated at least once. That's what it means. Is this clear? Any doubts with the solution? I understand that this is very easy. The next problem is not going to be not so easy. So I just in every class I usually take an easy problem in the start and then I move on to the harder problems. Is that clear? Any doubts with this so far? So people who have come newly, I'll just reiterate the question. There's a ribbon of length n. You want to cut it into parts of length either a, b or c. So after cutting, the number of ribbon pieces should be maximum. Like you want to cut it into maximum ribbon pieces as possible, but with the constraint that each ribbon piece, the length of each ribbon piece has to be either a or b or c. So what did we do? We just assume that there's going to be, wait once, yeah. There's going to be x a's, y b's, x ribbons of length a, y ribbons of length b, and z ribbons of length c. So we figured that since the constraints are low, like about 4,000, we could do 4,000 square and that would still be under our time limit. 1 second. All right, x into a, y into b, z into c. Now we just iterated over x and y, and we figured out z because we know all the other variables. We can figure out z. You can figure out z easily, which means since we know x and y and z, we figured out z, x and y, we know z. And once we know x, y, z, we take the maximum of all x, y, z's. We brute force over x, we brute force over y, and we found out z if it's valid. Like, see if yeah. Is this clear? Any doubts so far? Any doubts so far? Very straightforward, and complexity of this is O n square, 2 loops O n square, right? Let's make a small optimization here. Can we do this better? Turns out we can. So what do we do here? Like, there's a method, like we can do it in dp, we can do it with dp. Like, for example, let dp of I be the maximum number of paths for I. So dp of I is essentially from I can be obtained from I minus a, from I minus a, I minus b, I minus c, right? So that's it. That's the answer. Like, you take the maximum of all the three. For example, if you want, if n is equal to 7 and a equals 2, b equals 3, c equals 4. So answer of 7 is equal to 1 plus answer of 7 minus 2, answer of 5, answer of 4, 7 minus 3, answer of 3. And similarly, because see, 7 minus 2, the problem link is this 1898. So from 7 you can either remove 2 or 3 or 4. If you remove 2, you'd have answer of 7. If you remove 3, answer of 4, answer of 3. Similarly, this is going to call answer of 2, answer of 3, answer of 2, answer of 1. Maximum of all of this plus 1. I'll show you a tiny example where we can compute this. So say given, let's take the example given here itself. Well, they're too simple. Let's take another example. 10 in terms of 3, 4, 5, or rather 15. Let's take 15. Let's compute the tables one by one. And A is 3, 4, 5, ABC, ABC. So this is 0. For 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So dp of 0, like, you can do it with just 0 cuts. You can't do better. For 1, the answer is you can never do it. The answer is minus infinity. For 2, minus infinity. For 3, you can do 3. How? You can do it in 1 cut, right? For 4, you can do it in 1 cut. For 5, you can do it in 1 cut. All right. From 6, answer of 6 is 1 plus maximum of answer of 3, like 6 minus 3, 6 minus 4, or 6 minus 5. 1 plus maximum of these 3, right? So your best shot is to choose 3 because the other 2 are minus infinity. 1 plus 1, which is 2. For 7, you can either choose to go to 4, or you can choose to go to 3, or you can choose to go to 2. 3 options. You can either, if you remove 3 from 7, you get 4. If you remove 4 from 7, you get 3. If you remove 5 from 7, you get 2. You can see that from 4 or 3, you're getting the same answer. So 1 plus 1, 2. Let's check for 8. What is 8 minus 3? 5. Maximum of answer of 5, which is plus 1, 2. Maximum of answer of 4 plus 1, 2. Answer of 3 plus 1, 2. The answer for this is 2 as well. Now for 9. answer of 9 is equal to 1 plus maximum of answer of 6, answer of 5, answer of 4. 5 is achieved from 9 minus 4. 4 is 9 minus 5. 6 is 9 minus 3. Because 3, 4, 5 are the only things that you can take. Correct? Yes or no? Any doubts so far? We can see that answer of 6 is 2, answer of 5 is 1, answer of 4 is 1. So answer of 9 would be maximum of this, which is 3. You can see that this corresponds to 9 is basically 9 is coming from 6 and 6 is coming from 3. 3 is coming from 0. It's basically a jump of 3, 3, 3. Right? Similarly, you'll get this 3. You'll get 3 here as well. Here you're going to get 4. Like, and this is going to call this, this and this. Similarly, 12 is going to call maximum of 9, 8, 7. So on. You're going to get 4, 4, 4 here as well. And here you're going to get 5 if you look at it. Okay? Awesome. Let's just code this then. It should be very easy to code this as well. Let's declare it with minus n, minus 1e9. Oh, devastator. Good to hear that. dp of 0 equals 0. Which college though? For int I equals 1, I less than equal to n, I plus plus. If I is greater than equal to a, dp of I equals max of dp of I minus a, comma, dp of I. Similarly, b. C. Very straightforward. So if you subtract a from I, you get this equation dp of I minus a plus 1. If you subtract b from I, you get I minus b plus 1. If you subtract c, dp of I minus c plus 1. Now in the end, you just want to dp of n. That's it. That's how quickly you're doing it. Right? Any doubts so far? This should be convenient, right? This is a very, very, very straightforward. It's a small approach. That's all. It's a small code and a small approach as well. Any doubts so far? Any doubts so far? Awesome. 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 Is there anything that's bothering you in this problem? I can move on to the next problem in that case. Vinay asks, oh, Vinay, you're back. So Vinay asks, why is dp of 0, 0? Because dp represents the, it's essentially, I'll just write max ribbon cuts. So a length of a rubber band of length 0 cannot be divided anymore, and like there's no, you can't cut it further, right? Like there's nothing there, so that's why. So 0 cannot be divided into 0, not divided, sorry. There are 0 means there are no ribbons anymore. That's what it means. That's why 0. Like, for example, if you want answer of 3, you ask answer of 0 plus 1, right? So mathematically, what do we want to know? We want to know a plus b, ax plus by plus cz equals 0. What is the maximum value of x plus y plus z? All the numbers are non-negative. So the x plus y plus z can only take 0. It can't take any other value. That's why I put 0. Is that clear? Any doubts with this? This is an O of n solution. Awesome, awesome. All right, let's go to another problem, a fun problem. Just finding it out, right? One sec. Just digging that problem here. Awesome, here's the problem. It's an E problem, but it's not a typically hard E problem. All right. Awesome. So let's take a look at this question. You're given a tetrahedron. Let's mark its vertices with letters A, B, C, and D correspondingly. An ant in the vertex D of the tetrahedron is standing at vertex D, standing on this D. The ant is quite active and he wouldn't stay idle. At each moment of time, he makes a step from one vertex to another vertex along some edge of the tetrahedron. Note that the ant just can't stand in one place. So you don't have much time to solve the problem. Your task is to count the number of ways in which the ant can go from initial vertex D to itself in exactly n steps. All right. In other words, you're asked to find the number of different cyclic paths with the length n from vertex D to itself. As the number can be quite large, you should print it modulo 10 power 9 plus 7. Awesome. Let's discuss what the question is. Let's discuss what the question is. So you're given a tetrahedron. Tetrahedron is basically a complete graph of vertices 4 in this case. Anyway, we're starting here, D. So the question asks, you're starting here. At every moment, you always move through one edge. You either go here, or you go here, or you go here. Right? Awesome. Now, after exactly n moments, you need to reach here. So there can be multiple ways you can reach D, like you can go here, 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 and then come back to D. There can be multiple ways to reach D. After exactly n moments, you cannot stay at a place for more than a moment. Like at a moment, you can stay at only one place, and then the next moment you need to move to a different place. Got it? Is that clear? Okay. N moments. Now, and at the nth moment you need to be here. For example, if n equals 2, you can go to D, B, and then D, or you can go to D, C, D, D, A, D. These are the only two options. For n equals 1, the answer is 0. N equals 2, the answer is 3. N equals 1, you need to move somewhere. You can't be at D. So there is no way you can be at D after one step, right? Is the question clear first of all? For n equals 3, the answer would be, let's see what the answer would be for n equals 3. So D, A, C, D. Note that D should be in the start, D should be in the end. Like for n equals 3, let's look at how the solution is going to look for n equals 3. And in between, D cannot come here, D cannot come here either, right? It cannot come here. Because if D is here, then D has to be here again, which is not possible. It's a contradiction. So here, we should have two other characters. It can be BC, or BA, or AB, or AC, or CA, or CB. Basically, all the 3 into 2 possibilities. So the answer for n equals 3 is 6. N equals 1 is equal to, it's 1, it's 0. N equals 2, 2. N equals 2, the answer is 3. N equals 3, the answer is 6. and I don't know what the sequence is going to be. It's probably going to rise up. It's going to rise up exponentially, but we don't know what the sequence is going to be. All right. Is the question clear? Is the question clear? Any doubts in the question? For a large n is up to 10 power 7. You need to find the answer for this. So you can't just enumerate cases like this with your hand. So you need to find an algorithm here to find this. So how would you do it? How would you do it? How would you do it? How will you do it? Now you might think for anything like that might not be so correct, because you might think the first and the last positions are fixed, but no. Why? The middle positions can also be D. What I mean to say is, if n equals 5, for example, this is an option. D, A, D, B, D. This is an option. So D can be in the mid. D it can be this, right? That's 5 steps. You're back at D after 5 steps. So not possible, right? So how do you do it? How do you do it? All right. Let's try to look at it in terms of a matrix. Let's try to look at it in terms of a matrix. Now, initially, the number of ways to reach D in 0 turns, let's call this 1. Number of ways to reach D in 0 turns. Let's label the other ones as 0, 0, 0. Or rather, let's make it a bit more nicer. Number of ways to reach D in 0 steps is 1. The number of ways to reach the other nodes A, B, C in 0 steps is 0. In the next step, in one step, the number of ways to reach a node other than D is basically 3, right? Because you can go here, here, here. There are 3 ways. But the number of ways to stay at D is 0. Okay, so far we have this. Now, next, from here, this is 1 step. This is 0 step, sorry. 1 step. Next 2 steps, second step. The number of ways to reach. So in 1 step, you can be at A or B or C, and the number of ways to be at D is 0. Now, after the second step, what is the number of ways to be at D? Like here, the first element denotes the number of ways to be at D after I steps. Like here, 0 steps, the number of ways to be at D. At 0 steps, at the 0 step, you are at D, and you can't be at A or B or C without making a step. At 1 step, what are the number of ways to reach D? At 1 step, what are the number of ways to reach a place other than D? There are only 2 places, 2 things here: D or not D. D, not D. D, not D. Meaning A, B, C. I'll tell you why this matters right now. Okay? Please let me know if you're following so far, or if there are any doubts. Second step. So, second step, what are the number of ways to reach D? This 3. So, you can reach D only in one way. Like, you can either reach it from, there are 3 ways to reach a place other than D. So, the number of ways to reach D is basically or the number of ways to reach d, at I is basically number of ways to reach not d at I minus 1. Is that correct? Because if you want to reach d at a step I, you should have to be at a place other than d in step I minus 1, right? Awesome. Let's do that. Now, that's basically number of ways to be at d at second step is basically number of ways to not be at d, like which is basically 3 at first step, which is basically 3 here. 3 comes here, and there's no other way, right? Now, what would this be? This is a bit tricky. What would this be? What would this be? So we need both these values, 2 or 3. All right, let's discuss what. So here, number of ways to not be at d, like number of ways to be at one of a, at b, and c. We're not telling which one. We don't care which one. We just want to know which one. Like if it's a d or if it's not a d. So number of ways to not be at a d at ith step. Number of ways to not be at a d at ith step is equal to, say in the I minus 1 step you're at d. Let's call the previous one as x and y. Previous one at I minus 1. Let's call this as nx and ny, nu x and nu y. So we know that nx is equal to y, meaning 3 was equal to this value. Like the new number of ways that you want to be at, you can be at d. The new number of ways that you can be at d at step I. I'll write this more clearly. I should write this more clearly. Okay. Yes, that's one way to look at it. Total minus number of ways to d. That's absolutely one way to look at it. I'm just trying to find a recursive way so that it's easier. So they say at I minus 1 is this. It's this x and y. You want to move to I. Nx, ny. Nx equals y. We know that because you can't move from d to d in one step. You have to move from here. And if you're at either b or a or c, you have only one choice to go up, right? There's only one edge leading to d. So nx equals y. Now ny, you can directly write this as 3 power I minus y, as Avinash suggested. That's one way to write it. I want a more recursive way to write it because this is one way. You can do this, like you can do this and you can keep computing each one matrix one by one. I want to progressively teach you something else, which ny equals, you can either go from d, which is basically d to any of those 3 and you'll land at a not d, 3x plus from y, if you're at any of these y, if you're at c, you have 2 choices. If you're at b, you have 2 choices. If you're at a, you have 2 choices. So 2y, which is also equal to 3 power n minus y, 3 power I minus y. I'll tell you why. We'll get to that later. Okay. Is this clear so far? Is this clear? Is this clear? Can you see what's going on here? Any doubts with this? Do you want me to re-explain this part? Any part of this, like how did this come? 2i might not be so easy to understand, but let me know if you want me to re-explain this. Is this clear? Vinayak, could you just let me know if it's clear? Yeah, okay. So, nx equals y. This part must be clear, meaning at so I do mass what's my peak rank. So I mean, rated round I got second once, but that's div 2 again. So and rating, yeah, in div 2 I got second, but yeah, that's my best rank, but that's again div 2, so might not be so representative. In div 1 I got something around 60 or something once. That's my best rank. So okay, this is basically D, not D. So the number of ways to reach D in I steps is basically number of ways to reach not D in I minus 1 steps. This must be clear, correct? Okay. Now number of ways to reach not D, like you want to be somewhere, any of these basically. Any of these. So it's basically 3x. 3x basically, if you're at D previously, now you have 3 choices. But if you're at not D, if you're at a not D place here, say if you're somewhere over here, for example, at A, then you have only 2 choices, right? That's why 2 into the number of ways you can reach a non-D place. From a non-D place, you have only 2 choices to go to a non-D place. From a D place, you have 3 choices. From a non-D place, you can't go to itself. That's not an option. You either go to D or 2 other non-Ds. You either go to D, from Y you either go to D or 2 other non-Ds. This is when it goes to D, a non-D to D, to D. This is non-D to non-D. Sorry, non-D to D, non-D to non-D. This is D to non-D. D to non-D is basically 3 ways. Not D to not D is only 2 ways. Like if you're here, there are 2 ways. If you're here, 2 ways, here 2 ways, so on. Is that clear? Is that clear? So what do we have here? We'll discuss how to write this in form of a matrix. So x, y becomes y 3x plus 2y. This is at step I, this is at step I plus 1. If you've seen my second video about binary exponentiation and so on, matrix exponentiation, you can see this, you can see what I mean about matrix exponentiation and so on. Especially binary exponentiation and applications, I think. That's the right video. You will see that, you can see that this can be transformed into a matrix, x, y. If you write a matrix, what is the matrix here? X into, sorry. If you apply this matrix, 0, 1, 3, 2 on x, y, you get 0 into x plus 1 into y, which is basically y. 3 into x plus 2 into y, 3x plus 2y. So if you apply this on I minus 1, you get I, right? A linear transformation. That's what it means. After one transformation, you get I. If you do 2 transformations, you get I plus 1. If you do n transformations, you get I plus n minus 1 or something like that. You get the gist, right? So initially this is 0, initially this is 1, 0, right? In the like 0th state, this is 0. So if you do one transformation, you get, let's say this is m0, you get m1. If you do 2 transformations to this, you get m2. Like if you multiply this again, 0, 1, 3, 2. If you apply this on this, you get m2. If you apply, for example, and if you apply, this is basically multiplying 2 matrices, right? If you apply, so basically, let me tell you more clearly. What is a matrix? One second. So you have this, right? you have 1 0 initial state. Basically, let's call this M0. If you apply this matrix A, 0 1 3 2, that is the matrix, right? We get M1. For example, if you apply this on this, you can see that you're going to get 303. So on, right? Now, if you apply A into A M0, you apply A to this, which is basically A into M1. This is basically M2. A into M1 is M2, right? And so on. So A, we know that we can write this as A square into M0. A into A to M0, M square. So A square into M0 will give you M2. Similarly, A power n into M0 will give you Mn. So we can simply calculate A to the power n, matrix power n, A power n quickly, and apply to M0. And by applying it to M0, we'll get Mn. That's it. Once we get Mn, we just need to find what the topmost element is, because we want to know number of ways in which the ant can go from the initial vertex D to itself. Meaning, we want to know the topmost element here. We want to know what lands here, basically. After doing A power n, wait, it's gone. Yeah. Interesting. 1 minute. Yeah. Yes, exactly. That's correct. Is that clear? A power n into M0 is equal to M power n. That's it. So first we calculate A power n. Say we get A, B, C, D, and then we get, once we calculate this, we apply M0. What is M0? 1 0, right? 1 0. So what do we get if you apply 1 0? We'll get A plus B, A into 1 plus B into 0, and denominator plus B into 0, which is basically A. C into 1 plus D into 0, we get C. And we just need to print A here. Basically, we can find A power n and simply print A. Is that clear? Is that clear? Any doubts so far? Any doubts? So let's do this then. So vector int A equals, what is the matrix? We just write the matrix. The matrix was, I think, 0, 1 and 3, 2. Right, this is the matrix. Awesome. Now let's write a function for multiplying two matrices. Vector int multiply vector int A I'll just, since we know that it's a 2 by 2 matrix, I'm going to create a 2 by 2 matrix itself. I'm not going to take the hassle to. All right. For int I equals 0, I less than 2, I plus plus. For int j equals 0, j less than 2, k less than 2, k plus plus. Ret of I k plus equals. This is just basic matrix multiplication. I'll just make all of them longs because the answer can get exponential. So yeah, return ret. right? Now we need to calculate a power n. First we're given the integer n, like, or well, let me write const mod. Like, okay, like just ignore the const for now. Mod is 10 power 9 plus 7. Now scene n vector in current vector. Initially it starts with the identity matrix. Let's start with the identity matrix. This is basically a power 0. A power 0 is the identity matrix. Alright, current to identity. While n minus minus current equals multiply current comma a. CR current 0 0. That's it. Yeah, that is it. Is that clear? Is that clear? For example, you can see that for n equals 4, n equals 4, I run this, I get 20, I get 21. I mean, sorry. Oh, yeah, nothing's there in the output. I get 21. Straightforward, right? 21. You can see that the answer is 21. Anyway, all right. So what happens here? What's happening here? I'm multiplying two matrices. Now this is basically current will have a to the power n. Now we just decided that we're going to print the first element, because that's what's going to be. We just need the topmost element, or you can multiply it by this and print the first element. That's okay too. But we just need the topmost element, the first element, because when you're multiplying this by this, a into 1 plus b into 0, a is going to land in the topmost element, and the topmost element is basically the number of ways you can land at d after exactly n steps. Is that clear? Any doubts so far? Any doubts so far? Any doubts? Please let me know in the live chat. So the complexity of this would be n. The complexity of this would be O of n into whatever the multiplication complexity is, which is basically 2 into 2 into 2, 8n. All right. Can we make this quicker? Yes, we can. So what we do is, we do it in a binary exponentiation fashion, like just how you do a power n. We write power of a comma n. We write what power means. Vector ll power vector ll a int n. So if n equals 0, return the identity matrix. Note that identity matrix is simply a power 0. A power 0. In other words, it's a matrix in which a, b, I equals a power 0. Anyway, that's enough here. Now, if n modulo 2 equals 0, then vector int, I'll just write odd, I'll write vector int. I'm writing too many vector, declaring too many of them. It's becoming a bit verbose, but okay. Vector int x equals power of a comma n by 2. Now, if any n is even, then you can just return x into x, multiply x comma x. Else, return multiply x comma x and again multiplied by multiplied by, yeah, because if n is even, a 0.5 is shaved off here, right? So if you multiply x, like if n is 7, x would be a power 3. Multiply x comma x would be a power 6. So if you want a power 7, you need to multiply an a again. Is that clear? Any doubts with this so far? Any doubts with this so far? All right, this is the complexity of this would be O of log n into like whatever the computation for multiplying is, which is a constant. So is this clear? I'll show you another shorter code for n equals 10 power 7, which is like, it's a small code, but it's going to be on, but still it's something. It's a small code. So is this clear? Any doubts with this? Do you want me to re-explain some part of it? The problem link for those interested is 166. Oh, here we haven't initialized it because like we don't need it. Like this is the initialization if you look at it closely. Like when equals 0, it's returning. Like this will directly return a power n. This will directly return a power n no matter what. Once you return a power n, you want 0, 0 element, right? 0, 0 element, because a is what's going to come here anyway. That's why you don't need to initialize it. Like you're directly putting it into current. You're not using current anywhere except printing the answer. Is that clear? Any doubts so far? Is there any part you'd like me to re-explain? Is there any part you'd like me to explain? Please let me know if you have any doubts. Was that clear, Vinay? Was that clear? Awesome. Man, it's cold here. Okay. Okay. So, what now? So, I'll just show you another like tiny trick in the sense that there's another way to do it. Like, you can scrap all of this for now. Mod is required. Like, this is the editorial approach. So, LL A equals like D ways equals 1, non-D like D equals 1, ABC equals 1, like I'll just write D and non-D, D equals 1, non-D equals 0. For int or like for int I equals 0, 1, I less than equal to n, I plus plus, LL new D equals non-D, LL new non-D equals 3 into D plus 2 into non-D. That's it. Now D equals new D, non-D equals new non-D, C or D. Is that clear? So what happened here? We did the same thing, but in a really short code. What did we do? It's going to be O of n, of course, because you can't have the cake and eat it too. And what's happening here? So if you look at it closely, like this is the number of ways to get D in 0 turns. In 0 turns. So far in 0 turns. 0 turns. Now this you're computing in I turns. In I turns, it's basically new D. We decided, right? The new D is going to be same as the old non-D. For new D for I, the number of ways to reach D at I steps is going to be equal to the number of ways to reach non-D at I minus 1 steps. That's what you're doing here. This is basically the matrix, nothing else. You're applying the matrix like the old matrix. I'll just write it down here. Old equals, I'm just going to write. Old was D. Old was D, non-D. New is non-D, three into D plus 2 into non-D. Do you see what's being done here? So for this matrix, if you apply this the matrix that we transformed previously, like 0, 1 and 3, 2, that matrix, you get the new thing. That's what you're doing here. And we're writing in terms of code. That's it. Alternatively, as Vinay previously suggested, the total number of ways after n turns. This is simply, this can also be written as 3 to the power p, power of 3 comma I. At I turns, you'll have 3 power I possible. That's the total number of, that's the total count essentially, 3 to the power n. That's basically 3 to the power I minus new D. You can write that. So you can keep another variable to keep track of LL. P3 equals 1. At each step, P3 multiplied by 3. Now new non-D is equal to P, the power of 3 minus new D. This works too. Any doubts with the solution? Any doubts with the solution? Is this clear? Ultra Instinct asks, sir, do you always prove greedy solution? Nope, I don't always prove greedy solution. For example, in a contest, you have less time, and sometimes proving greedy solutions can take a while. That could be an exercise for after the contest, but during the contest, I try to make a strong reason for why the solution is correct, but I don't prove it, and I don't think a lot of people prove it either. If it strongly speaks to you, then go ahead and code it. If it doesn't speak, like after the if you see there's a wrong answer, then you have a feedback to your mind saying, okay, my intuition was not correct, so I need to modify it here. I don't always prove a greedy solution, if that's what you ask. Is this clear? Any doubts? Is there any problem or something that you want me to re-explain? Or do you have any questions for me? If you have any questions for me, please let me know in the live chat. So is this clear? Awesome. If you don't have anything else that you want to ask me, I guess I'll just revise this problem once again and decide and figure what we did. Go through the code once and then. Oh man, okay, okay, I'll just, sorry for the, yeah. 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 Awesome. Ultra Instinct asks the various ideas in greedy, how to get good at it. So you don't get good at it, like it's you just increase the probability of solving it, like how to get good at it, I don't know. My answer is going to remain the same for every question, every such question, and it's practice. Sorry. Yeah, as I said previously, there is no set of questions that you can solve to be perfect and greedy. There are just a lot of possibilities. The idea is to keep solving a lot of problems so that you can train yourself to solve new problems in general. Yeah. Just solve problems that are at your threshold level. Yeah, I know the answer is pretty disappointing, but I don't want to lie with a satisfying answer. So, yeah. And okay, yeah, sorry about that. Anyway, so what do we have here? Like, what did we do in the question? First of all, the question was you're given a tetrahedron and you're at starting position D, and you want to reach from D from n steps. At each step, you're going through an edge, and you want to know, like, you have multiple choices at each step. You have 3 choices to be precise at each step. You can either from a given cell, from a given node. From a given node, you can go to the other 3 nodes. So at each step, you have 3 choices. So what did we do here? Like, first of all, what is the question? The question was, now we have so many choices, and after n turns, you'll have like 3 power n choices. That's a lot of choices, and you want to know, out of those 3 power n, how many of those choices will land you at exactly D after n steps. Now to do that, what did we look at? Like, we found, like, we tried to find at each step how many ways to reach D and how many ways to reach a node other than D. Now, once we decided that we want to find this, we try to understand how is it related to a previous, how is step I is going to determine, it's going to single-handedly determine how step I plus 1 is going to look like. That's what we used. we precisely looked at each case. Like at step I, if you're at D, you are going to go to a place which is not D at step I plus 1. And at step I, if you're at a cell which is not D, you can still go to a step which at a place which is a non-D. For example, if it's at A, you can go to B or C. If you're at B, you can go to A or C. From a non-D, you can go to a non-D, but you can go to a D as well. So the new number of ways you can go to D is going to be the old number of ways you can be at non-D. That's done. The new number of ways you can be at non-D is the old number of ways you can be at D plus 2 into the number of ways you can be at non-D. We just wrote that and we decided that, right? And from that we figured a recurrence, and with that recurrence we found like which matrix fits in well. We found a matrix that fits in well. And applying that matrix to step I minus 1 gives you step I, meaning applying it to step 0 gives you step 1. So applying it to step 1 gives you step 2, which means you're applying that matrix twice on step 0 gives you step 2. Applying it on that step 0 n times gives you step n, like basically the answer for n. Applying it the matrix n times means multiplying those matrices, like applying this matrix on another matrix, meaning it just means that a matrix multiplication for that definition of multiplication, right? So once you're applying that, you calculate what a power n is. Now we know a power n, it's not just limited to integers, like integer multiplication is related to a lot of multiplications, right? A lot of other operations as well. So we do that. We do a binary we calculate a power n quickly using binary exponentiation, and once we do that, you know what the matrix is now. Now that you know what the matrix is, you just you multiply it by the a0, like the initial state, which is basically if you just write it down, you'll figure that the answer for this question, the answer for this would be the 0,0 cell of a power n, and that's what we printed, and we saw that we got the correct answer as well. Now to get a shorter code, that's what we did, right? A power n, power of a comma n. This is straightforward binary matrix binary exponentiation. After this, you multiplying. This is basic matrix multiplication, which we all know. Identity matrix is basically we want to know a way to represent a power 0. We want to know a way to represent a power 0. That's basically it. And this is our matrix A, which are repeatedly multiplying, rather smartly multiplying, to get this answer quickly in log of n. A power n, and after writing a bit, we found that the answer is a current of a0, like the matrix a power n's 0, 0 the element, right? Then we looked at a smaller way, like a really sneaky way. Yeah, this would give us our answer as well. It's barely a 10-line code, right? This is non-D and this is D. Like old D, this is how old non-Ds affect D, the new D. It's just directly putting it there. Otherwise, this is the other option. So if you look at this closely, new D plus new non-D is equal to, if you just add them up, you get 3D, like here, 3 into D plus 3 into non-D. Meaning, if you look at it closely, this is basically 3 into non-D plus, right? So the new D plus new non-D is being multiplied by 3 every time, meaning that's basically the total number of ways. That's another way to look at how you get 3 power n in n terms. Each time, initially new D plus non-D is 1. At the first step, D plus non-D would be 3, then it will be 9, it will be 27, 81, so on. It will keep going on in powers of 3. Is that clear? Any doubts with this so far? Any doubts with the question, or do you have any questions for me? I can answer them, or otherwise we can we can end the class. Awesome then. I guess let's end the class then. Like, so this is a Telegram channel again. So if you want to have live updates on latest classes and so on, join the channel. And if you found this video useful, or if you found the content any useful, don't forget to drop a like so I know you understood it. And if you think it's going to be useful for your friends who just started competitive programming, do share it with them. And if you want to get latest updates on if you want updates or notifications on the latest classes, do click the bell icon and don't forget to subscribe. Awesome. It was nice talking to you, and have a nice weekend. I'll be teaching tomorrow as well, likely, if everything goes well. All right. Great. Bye. Have a nice weekend.